Hello, everybody. Welcome to our webinar series, Machine Learning for Operational Forecasters. My name is Milana Vučković, and I will be your host today. And today with me is Linus Magnusson, who will present in a minute. As in previous webinar in this series, we have also a couple of colleagues online who will help us in answering your questions in chat. So this is the third webinar in our series, and today we will see the example of case studies with machine learning models. So over the years, over the past year or two, we have organized several webinars and trainings around development of AI models at ECMWF, but they were mainly technical and about models themselves. And in this series, we want to give you more of an operational perspective, to give you, operational forecasters, information that you need to know in order to use ECMWF machine learning model output effectively. So the main goal of this webinar series is to encourage you to use these machine learning products and to give you the helpful information and to encourage you to give us feedback on how you use these products and how they work for your area. If you have any questions during the talk, you can put them in the chat. And yes, we have several colleagues who will answer. And also you can put your comments about your use of machine learning data in your organization, because we want to know how you are using these models. In the first two webinars, we showed you some basics on machine learning models and where to find the data, where to find the charts, and some verification aspects. And now, in the third and final webinar in the series, Linus will show you a few case studies that we have analyzed since we started running our AIFS models. This webinar is being recorded, and we will upload it to YouTube in a couple of days. And also one practical mark, when people start, if somebody starts asking questions in chat, you might hear pinging. And if you want to, if it's annoying, you can mute the chat during the webinar so you don't hear too much pinging. And you will still see messages, you will just not be notified about them. So this is enough information from me. And with this, I give the floor to Linus to present.
Thanks, Milana, for the introduction. And as was said in the introduction, after seeing the basics about the machine learning and the verification, we are today going to look at example of case studies that me and my colleagues at ECMWF have investigated over the past years and that we have picked up during our daily monitoring. And that will show some examples of the performance as a complement to the verification results. But as a recap of the previous webinars, and for you who missed it, here's an overview of the current forecast system we run at ECMWF. So for the physics-based AIFS model, we're currently running 3 systems. So we have the mid-range ensemble, which runs with 9-kilometer resolution out to 15 days with 5 ensemble members. Then we have the sub-seasonal forecast that we run with roughly 36-kilometer resolution once a day out to 6 weeks lead time and 101 ensemble members. And then finally, once a month, we run the seasonal forecast out to 7 months. But in this webinar, we are going to focus on the mid-range performance because that is what we currently use the machine learning based forecast system AIFS for. So we are going to talk about both the mid-range deterministic AIFS Single and the mid-range ensemble AIFS Ensemble. And both of them are running out to 15 days lead time with roughly 25-kilometer resolution. And if you remember from the previous webinars, there were discussions about the loss function, where we use a mean absolute error loss for the AIFS Single, which favors a bit of smoothness in the forecasting field to avoid double penalty effects. While for the AIFS ensemble, we use a probabilistic loss of the CRPS score in order to favor ensemble spread or get a good, well-calibrated ensemble spread. So if we first have a glance on the forecast valid from today, from roughly 6 days ago, just to get an impression on how this forecast looks, we can see the AIFS control forecast on the top left, so the physics-based, then the AIFS single top right, and the AIFS ensemble control bottom left. Then we have the half-day forecast from IFS as a proxy of the outcome. And what's dominating the weather today is the trough going down towards Italy, where you can see a lot of rain in places in the current short-range forecast. And this feature was already present in all the 5-day forecast, although the precipitation structure are quite different. And that's expected also if we were going to look at an ensemble system, because we have the uncertainties. But what you can notice if you look at the top right for the AIFS single, that the precipitation field is a bit smoother than we see from the IFS control top left. And that was, as I said, due to the training of the data the loss function used. But when we look at the AIFS ensemble control, we again gain the details of the precipitation field. So at least from my eye, it's hard to see a difference in the type of spatial scales between IFS control and AIFS ensemble control. And just a reminder, if you're interested in the verification results, you can look at on the ECMWF webpage, where we update after each season a range of different verification metrics for these models. But as promised, this webinar we will look at the weather cases, and focusing on extreme weather. And these cases are picked from the ECMWF severe event catalog, where we save evaluation results for a selection of severe weather events over the past season. And we have been doing this for more than 10 years now, so it starts to be a quite wide range of cases included in this catalog. So the case I decided to start looking at is the tropical cyclone Umberto and Imelda that later triggered the extratropical cyclone Amy that hit in northwestern Europe in beginning of October with strong winds and precipitation. And this was a fairly complex situation. And on this plot, I've stacked analysis based on the IFS data simulation on top of each other, starting from the 30th of September, and then the bottom two is going up to the 4th of October. And if we start from the top left, we can see in the corner that the tropical cyclone Umberto entering the plotted domain. And later we see the tropical cyclone Imelda, which was located very close to Umberto and started to interact with each other. And what happened later was that fairly close to the low pressure center of the ex Umberto, another cyclone formed that was later named Amy, that quickly moved to the northeast and approached Ireland and UK late on the 3rd of October with severe winds. So as you can see, it was a quite complicated picture to forecast, with a lot of interactions between different synoptic systems and a rapid development. So now if I switch to a forecast from the AIFS Single, initialized from the 30th of September, but with the panels valid at the same time as the analysis. You can see that this evolution was very well captured in the AIFS, from bringing in the 2 tropical cyclones into the subtropics and spinning off the cyclone Amy, and then have the rapid intensification towards Ireland and UK. So this is one of these things. When I first heard about the machine learning forecast, I thought that would more or less be impossible for the models to learn how to spin up a cyclonic system and get a rapid development. But we have seen a lot of cases over these past years that convinced me that it is actually something right going on in these models. And it is even more than that, because in this case, with the cyclone Amy coming up towards Northern Europe, and then later on triggered a ridge building, that was much better captured in the AIFS Single compared to the physics-based AIFS control. So what you see on these plots is in shading the day 6 error for the forecast initialized on the 1st of October, where you see a large blue and purple blob in the figure for AIFS control, indicating a large error. So the AIFS forecast missed the ridge building towards Scandinavia after Cyclone Amy. But the AIFS Single had, on this color scale, more or less a perfect day 6 forecast. So what this means is that it managed to avoid what we often refer to as forecast busts. And this could be visualized looking at the time series of day 6 errors over Europe for 500-year potential height. Here we look at anomaly correlation coefficient. So the higher the better, and the perfect forecast is 100% correlation. What you see on this plot that you can focus on is the AIFS control forecast in red and the AIFS Single in blue. And if we go to the start of the October, we can see a clear dip in the score for the red line, so the AIFS forecast. And that was what we saw on the previous plot related to this ridge after Amy, that it came from tropical cyclone Umberto and Imelda, while the scores were still very good for the AIFS Single. And if you look at other episodes during this autumn, when we have had tropical cyclones undergoing extratropical transition, we see, at least for after the tropical cyclone Erin, tropical cyclone Melissa, that we see this kind of dip of score in the AIFS model, but we do not see it in the AIFS. And we have seen, when we verify the tropical cyclone tracks themselves And this, the plot to the bottom right, is from last year, but for the North Atlantic, that we get better tropical cyclone tracks in the AIFS model. So what we see a hint of here, but we do not have any clear statistics yet, but that that with the machine learning based AIFS, that it from several cases seems to avoid forecast bust after extratropical transition of tropical cyclones, which have been a problematic area for NWP forecast for many years. And if we look a bit wider into large errors and the frequency of large errors or forecast bust, so if we base the statistics now for the root mean square, but still focusing over Europe day 6. So here the lower the better is. We see if we look at the histogram to the right, that a reduction of the frequency of very poor forecast in the AIFS in blue compared to the IFS control in red. So for some reason the AIFS Single manages in many cases to avoid these forecast busts. So now continuing to other aspects of Storm Amy, and we're going to start to look at the capturing of the maximum wind. So to give you an overview of how of the extent of the extreme, the plot to the right shows the extreme forecast index based on 1 day forecast from the AIFS ensemble. So when it's red, it's close to 1, which is the saturation level for the extreme forecast index. So you see a large part of northwestern Europe were covered by a quite high extreme forecast index. And the worst areas were Western Scotland. And if you look at the satellite image to the right, we can see a possible stingjet feature reaching Western Scotland on the evening of the 3rd of October. So if we compare the means level pressure and 10-meter mean wind valid at 80 UTC on the 3rd of October in the ECMWF analysis to the left, and 42-hour forecasts from IFS control forecast in the middle and AIFS Single to the right, we see that the pressure fields agree quite well with each other in terms of the position. But if we look at the shading, we see that we in the area with the most extreme winds, where we had this suspected stingjet feature, we see that we get into towards the black, gray and black contour scales in the ECMWF analysis and also the IFS control forecast. So that's reaching 30 meters per second or above. But that feature is not captured to the same degree in the AIFS Single. So to zoom in on this feature, I have made a fairly complicated plot to the left. But what we see here are symbols all representing forecast valid for 24-hour maximum mean wind in a 1 degree box on 12 UTC on the 3rd of October to 12 UTC on the 4th of October. And you can see in the map on the top write the extent of this 1.1 degree box. And inside this box, we had the station on the island Tyree, and that station failed. We broke down during this event after reaching 27 meters per second. So I expected at least to have had a maximum wind speed above that. So if we now go to this forecast evolution plot to the left, so we have the forecast initialization time on the x-axis and the maximum wind, which is a maximum mean wind and not wind gust, because we do not have a wind gust as output yet from the AIFS. So we base this one on 6-hourly output. We see for the short range forecast that we get much higher wind speed values from the AIFS control forecast in a red dot and the AIFS ensemble in blue box and whisker. If we compare it with the AIFS forecast, so the AIFS ensemble is in pink box and whisker, AIFS single in cyan dot, and AIFS ensemble control in yellow. So we see this big gap between those two, between the physics-based and the machine learning-based forecasts. And that's also visible if we make a quantile plot between observations of wind speed from CNOP observations on the x-axis and forecast values on the y-axis. So being below the 1-to-1 line means that the forecast in this climatological sense had weaker wind speed than the observations. And we can see for Storm Amy that that's true for especially the AIFS single and AIFS ensemble control in both blue lines. Well, for the AIFS, for the highest wind speed, got a better match with the observations. And this is based on stations below 500 meters, because when we get up to orography and up in the mountains, or the Scottish mountains, we would expect a larger discrepancy. And if we look at the same type of diagnostic, but based on the 3-month period, we again see that for the going towards the most extreme winds, that we get a similar frequency out from the AIFS model compared to the observations. So this is just comparing the climatological distributions of winds. So it's not saying whether it predicted it at exactly the correct place, but at least it shows that AIFS is currently more capable to get the most extreme winds compared to AIFS, and that's a similar conclusion as previous storms, Ciaran and Owen. And looking at these cases, it seems to be related to stingjet features or similar type of really extreme winds around cyclones. So now moving on, a couple of hours later for Storm Amy, and looking at the precipitation, I choose to look at the precipitation for southern Norway, where you can see the observations and the outline box to the right, and again the extreme forecast index for precipitation on the 4th of October to the left, where we see close to red values in large part of southern Scandinavia. If we start at look at snapshots of the deterministic forecast, so here we see 24-hour precipitation valid on the 4th of October in forecast from the 2nd of October, 0 UTC. From the observations top left and the AIFS ensemble control top right, then AIFS single and AIFS ensemble control to the bottom. And here you can see signs of the lower resolution in the two machine learning based forecasts, but the magnitude of the precipitation is similar for this event between the physics based and machine learning based. And that's also visible when we look at this forecast evolution plot, but instead of looking at the maximum wind speed, we're here looking at the precipitation in this box over southern Norway on the 4th of October. And here we can see actually much more similar evolution and magnitude coming out from the different forecast system. What you can note is that especially the cyan dots, so the AIFS single for the forecast initialized in the end of September into 1st of October, it was in the upper range of the ensembles, and especially compared to the AIFS forecast. And that was during the period I explained a couple of minutes ago in forecast that led to forecast bust in the AIFS forecast, but not in the AIFS single. So now we're moving on to a completely different event, and we're looking at the heat wave over Western Europe in August this year. And as with previous examples, starting with extreme forecast index based on a one-day forecast from the AIFS, where you can see that the heat waves, so with EFI values for temperature close to 1, cover large part of southwestern Europe into the Alps. And last summer, this part saw quite a lot of different heat waves. And on the top right, you can see for an area of southwestern France, how the 2-meter temperature evolved from 1st of May to 1st of September, where in thin lines are daily values and the thick line is the 7-day running mean. You can compare that with the climatology in dashed line. But in beginning of August, we had a dip back to kind of normal temperature for a couple of days before re-emerging of the heat waves. So we're going to focus on this emerging heat wave. If we first look at forecast, the short-range forecast from the different systems, valid for 2-meter temperature valid 12 UTC on the 11th of August, we can see a similar magnitude of the temperature. Actually, the AIFS single, and especially the selected here, the first member of AIFS ensemble, was given slightly higher temperatures than the physics-based AIFS ensemble control. And if we look at this type of forecast evolution plot again, for so showing all forecast valid last of August 12 UTC around Toulouse, France. We see for the short range that all the forecasts compared quite well with the observations, which are put in the green symbol are put inside a black circle. but we can see a bit more ensemble spread actually coming out from the AIFS ensemble in purple. So we get, it seems to capture a bit more of the uncertainty. Then if we go backward in time and look at early initial times, we again see a similar evolution of the signal in all systems, but also again and quite intriguing if we look at the cyan dots, the AIFS Single was quite good in capturing this heat wave on an early stage. And that leads me into just to have a look on the verification of the forecast over Europe during June, July, or July into September last year. I had to start it on the 1st of July because that was roughly this time we introduced the AIFS ensemble in operations. So what I put to the left is for the 500-year potential light, and to the right the 2-meter temperature and the root mean square, with the AIFS control in red, AIFS single in brown, and then the ensemble means of the AIFS ensemble in pink and AIFS ensemble in cyan. And the other thing I did with this one was to start the axis from 0, and there you can see that comparing with the day 10 error for 500-year potential height, the day 1 error is quite small, is less than 10%, or rather towards 5% of the asymptotic value, depending on what system we look at. So during these 10 days, we have a lot of room for the loss of predictability. And we can see that the error up to day 6 is quite similar for AIFS single and the 2 ensemble mean, but the AIFS control forecast start to deviate and develop larger errors around day 4, day 5. If you look at the 2-meter temperature, on the other hand, we see that the starting point, so the day 1 error, is only of the order of magnitude being half of the asymptotic level towards day 10. So we start on already quite large errors in the short range forecast, which is to a large part due to biases in the forecasting system and the representativeness errors. So that one have to keep in mind when we talk about gains we see in the machine learning model, that's still relatively small to the absolute magnitude of the error of the 2-meter temperature. And I guess if I were doing the same exercise for 10-meter wind, it would look even worse. And again, we see that the AIFS single and the 2 ensemble system have a similar magnitude of the error up to day 5, day 6, while the AIFS control forecast develops a bit larger errors. So then we have spent some time to understand the difference in what situations the AIFS forecast gain skill or have a better performance. And what we looked into quite an extent after last winter was conditions with reasonably cold temperatures over Central Europe. Here's an example from the last of December with the 12 UTC temperatures. And this I recommend you to look at the blog post by my colleague Sofiane Karmouche with other colleagues on the ECMWF webpage. So what you can see in this situation was in the observations that large part of, especially southern Germany, were covered by temperatures below 0 degrees into the blue. And while this was fairly well captured by the AIFS Single, the 2-day forecast, we see in the physics-based AIFS control that the temperatures was much warmer. And when we looked at these forecast evolution plots, we here see a clear separation between the physics-based forecast in blue and red dots and the machine learning-based forecast in pink books and whisk and cyan dots. And we also linked this one to too few clouds, especially in the AIFS forecast, although we see in the forecast evolution plots for the especially the AIFS ensemble that is also underpredicted the cloud cover. So then with this hypothesis that it was linked to the cloud cover, we looked into cases during the past winter, but we separated the days over this area of southern Germany with cyclonic flow and anticyclonic flow. So what you see on this plot is biases on the 2-meter temperature to the top and low cloud cover to the bottom. And if we compare the AIFS Single and AIFS control for days with cyclonic flow, we see quite similar pattern with visibly low amplitude of the biases. Well, if we go to days with anticyclonic flow, we see a large temperature bias in the AIFS model. So that's the big red blob on the top right. We also see that it's underpredicted low cloud cover during these anticyclonic conditions. So what this shows is that during these cases with a blocking situation over Central Europe, where we as forecasters know that we quite often get low clouds and fog, the physics-based model struggles to capture the sharp inversion and the humidity in this sharp inversion. And if I think about this, it's a quite complex system to get the inversion right, the humidity right, and then the thickness of the cloud and the radiation properties. On the other hand, the machine learning-based forecast have learned the relation between the large-scale flow and the 2-meter temperature and might or might not need information about the cloud cover to get the 2-meter temperature right, because it has the statistics and the statistical relation to draw the conclusion from. But not everything is perfect in the AI-based model world. So here we show a coming slides a couple of known issues in the machine learning-based model, but we have to remember that the AIFS forecast system is still a very new model, and there's still a lot of improvement and to be made to iron out some inconsistencies. So the first example is cloud forecast. We see the AIFS control forecast to the top left, and then to the top right we see the AIFS Single, and here we see the cloud cover have a much smoother appearance. It's similar to what we saw for precipitation, but we also see in the statistics that it the AIFS Single lacks cases of completely overcast and also at some degree completely clear sky. So it's more in the middle of the distribution. In the bottom right, we see the AIFS control forecast, and here again, you see sharper colors, so getting more towards overcast. But then on the other hand, it has a somewhat blocky appearance that we currently investigate to understand why it looks different on that spatial scale. Another feature that we have seen in the AIFS ensemble is that during orography in warm areas, for example, this is from the summer and over Iran, it develop odd pressure pattern in the mean sea level pressure, and also can be seen in the geopotential field and to some degree in the temperature. We also this feature we see quite often also over the Andes in South America, but we have good hopes that this will be solved in the next version of the AIFS ensemble. Another feature we see is looking at snowfall in the AIFS ensemble. And this example is from the 22nd of August, where when a 2-day forecast saw a blob of snowfall over northern Norway. And even if it's August, in this case had northerly flow and over the mountains in Norway, it could potentially be snowfall. Then we also see a blob over the Alps, and that is probably a bit more questionable whether it was really going to be snowfall. But then when we go to the Balkans, and where it was 16 degrees at this point, and we see snowfall on the AIFS ensemble control forecast, that's definitely wrong. We also have seen snowfall coming out from tropical cyclones and convective showers in the ITCZ. Then is the question we get often about physical consistency, or what is the machine learning based model able to get all the consistencies between parameters. We've seen a couple of problems with that. In the beginning, the first version of AIFS, that we had precipitation, we noticed that the precipitation could go below 0. But now we have introduced in the training of the AIFS a way to avoid negative numbers of precipitation. But what we currently have currently see in the AIFS model, especially the ensemble, is that the 2-meter dew point occasionally and with a slight margin can go above the 2-meter temperature, which is an inconsistency, and also that the accumulated downward shortwave radiation at the surface can be slightly higher than the clear sky value. So we haven't introduced any constraint to this more dynamical physical limits. And one have to keep in mind, with more variables included in AIFS, we increase the risk for inconsistencies. So we'll keep a close eye in version 2.0 of AIFS, where we plan to introduce snow depth that is consistent with snowfall and temperature, and so on. And these issues we find we are documenting on publicly available pages, so non-forecast issues pages that we have both for AIFS Single and the AIFS ensemble. So that leads me to my summary slide, and hopefully giving you a flavor of the different characteristics of the physics-based and the machine learning-based forecast. And what we can say about the AIFS is able to make very skillful predictions of large-scale flow. And it captures extremes, but sometimes missing the magnitude of the extremes, such as the most extreme wind speeds to windstorms and in some sort of precipitation event. But we also see that it managed to improve conditional systematic errors that we've known in AIFS for a long time. And we will continue our effort to evaluate this system and find strange behaviors and find ways to improve them. And for extremes, one have to remember that AIFS is limited by the training data, so what ERA 5 is able to capture. So we have ongoing efforts to add observation data into the training. And then we'll also include more Earth system components such as waves in the future, higher temporal and spatial resolution. We are working on a sub-seasonal forecasting system and reforecast data, and we also experimented with hybrid model to try to see if one can combine the best parts of AIFS and AIFS. Let's stop then, leave a page with some further reading up.
Thanks a lot, Linus. Yes, all of these pages will be very useful, and also all of these analysis is very useful for the forecasters that will start using or have started using AIFS as their in their forecast. We have a few new questions if you want to have a go. There is another question. I'm especially interested in the evaluation of AIFS and AIFS on extreme events. Do you work on broader validation of AIFS and AIFS on extreme events?
Yes, we have ongoing work to do statistical evaluation of extreme events, and that's I see it as a complement in a way that for the most extreme events one have to look at cases, because we will not be able to get enough sample size to do statistical evaluation. Then one can make a statistical evaluation for different thresholds, such as look at the 99th percentile of the climatology to look at hits and misses, and do various kind of statistics like frequency bias. And then one can look at more the climatological properties to see if one get the same distribution functions. And an example of that was this quantile plot I showed for the wind speed. So that's the different paths we're currently undertaking.
Thank you. Next question is, do you also do evaluation of on sea level height of AIFS?
No, so we do not yet have sea level height as a variable, so we haven't trained that. So that will be in the future when we include more ocean components, but it will probably take a few updates before we are coming to such a variable. So in the next version we will have the ocean waves coming in.
So since there are no more questions, thanks a lot, Linus. We have been this webinar has been recorded, and we will edit it in the next couple of days and put it on YouTube. So with the other recordings of the previous two webinars. And with this, thank you all for joining, and thank you, Linus, for presenting, and thanks Thomas and Gabriel for monitoring the chat and answering the previous questions. Thanks a lot for joining, and see you maybe in some other webinar series.
Thank you.